Part 6 of Unit 2 is about advanced reaction types. The reactions that we look at in this video, they're more specific versions of single and double replacement synthesis and decomposition reactions. These are just some details that could go a long way towards helping you on the net ionics question on the AP test. Anytime you see a non-metal oxide and water, your product is always going to be an acid. Always going to produce an acid of some kind. So let's look at this example. Sulfur dioxide, that's SO2. It's bubbled through water. We know our product has to be an acid. Acids start with the hydrogen ion. These are all going to combine into one weak acid. We're going to have H2SO3. That's the sulfite ion, so this is sulfurous acid. It's a weak acid. This is the net ionic form of it also, because we had sulfur dioxide gas, liquid water, and this is a weak acid, so it stays written together. Anytime we have a metal oxide being added to water, we're going to produce a base. The product's always going to be a base. So in this example, solid potassium oxide is added to water. Potassium oxide is K2O. Adding it to water, we know it's going to produce a base of some kind. Bases, we know, end in hydroxide. And the only other cation in this reaction has to be the potassium ion. So KOH is going to be our base that's formed. This is not a balanced reaction. We've got to throw the coefficient of 2 in front of our product here. And this is not the net ionic form either. Potassium oxide is a solid, so it stays written together. Water is a liquid, it stays written together. But potassium hydroxide is a strong base. That means it dissociates. So we'd actually have to rewrite this as K2O plus water yields 2 potassium ions and 2 hydroxide ions. There are no spectators to cross out, but this is the correct form of the net ionic reaction from metal oxide and water. When we add a metal oxide to a non-metal oxide, our product is going to be an ionic salt, which is just an ionic compound. So in this example, solid potassium oxide added to a container containing, that sounds intelligent, to a container containing sulfur dioxide gas. This is kind of a combination of the first two reactions we looked at. We're going to be combining potassium oxide and SO2 into potassium sulfite, K2SO3. And you'll notice that we don't have any aqueous solutions mentioned at all, so we're actually forming solid potassium sulfite, so this is the net ionic form of the reaction as well. The reverse of those reactions is also possible. If we just flip them around, put the products on the reactant side, a base would break down into a metal oxide and water. An oxyacid, or an acid with oxygen, would break down to water and a non-metal oxide. And a salt that has oxygen in it can break down into a metal oxide and a non-metal oxide. Complex ion reactions, these are cool reactions to actually see happen. They form some really neat colored solutions. These are also called coordination compounds. Complex ion reactions typically take place between a transition metal and what's called a ligand. And here's some examples of common ligands: ammonia, water, hydroxide, thiocyanate, and cyanide. A ligand, it's an ion or an atom that has a lone electron pair that can be used to form a bond to a metal ion. So we know we've got lone electrons on nitrogen in ammonia or on oxygen in water. Those lone electrons are going to be attracted to and form a bond to one of these transition metal ions. These are the rules for writing a complex ion reaction. Usually you're going to have some sort of soluble salt of the transition metal plus the soluble salt of the ligand, and it's going to form the complex ion. To find the formula for the complex ion, you take the charge of the metal multiplied by 2, and that's going to be the number of ligands that attach to the central metal ion. So if our metal ion had a charge of +2, that means that 4 ligands are going to attach to that metal ion. And the overall charge of the complex ion, it's going to be the charge of the metal ion plus the total charge of the ligands. Not all ligands have a charge, like water can be a ligand, so it won't alter the charge any, but to find the overall charge of a complex ion, you just add the metal ion charge to the overall total charge of the ligands. So in this example, solution of cobalt-3 chloride combined with concentrated ammonia. Cobalt-3 chloride is our soluble salt. So we got cobalt plus 3, and ammonia is going to be our ligand, NH3. So our complex ion is going to form between cobalt and ammonia. So we're going to write it as CONH3. Now remember, the number of ligands that attach to the metal ion, it's twice the number of that charge. So it's +3 charge. That means there's going to be 6 ammonia ions that attach to it, or 6 ammonia ligands, excuse me. And the overall charge of this ion, we're going to add the charge of the cobalt and ammonia together, so it's going to be a +3 charge. Complex ions are often put in brackets just to keep them together and separate from other parts of the reaction. And we're still going to have our 3 chloride ions present over here. Those are going to be spectator ions, so they would be crossed out of our net ionic form. So the overall net ionic reaction would be cobalt plus 3 plus 6 ammonia is going to yield our complex ion. Cobalt NH3 6 plus 3. Your question for this section: write the net ionic equation for the following reaction. Solid zinc oxide is added to water.